our next section, which is quite short, is section 4.4, the condition number. Let's look at a linear equation ax equals b. Everything we say now will also transfer to least squares problem ax approximately equals b. Now, of course, a and b, as always, are given and x is to be determined. But often your right-hand side b is the result of computations that you did previously, and as such it has probably been affected by rounding error or other little errors. So probably b is a little bit wrong. Question is, how wrong might x be? So let's denote this new slightly perturbed right-hand side by b tilde and now solve exactly for that new right-hand side. And denote the exact solution of that problem by x tilde, which is the exact solution for the wrong right-hand side b tilde. And let's denote the error in the right-hand side b by delta b and the error in the solution x by delta x, and ask how large is that error in the solution resulting from the error of the right-hand side. And let's start with the so-called absolute errors, which is just the norms of these vectors themselves. So if you take the two equations ax equals b and ax tilde equals b tilde and subtract them one from another, then it's clear on the right-hand side you get delta b. And on the left-hand side, by linearity of a, you get just a, and then in brackets x minus x tilde, which is just delta x. And now you can express delta x in terms of the inverse of a and delta b, so that the norm of delta x equals the norm of a inverse applied to delta b. But of course, using the operator norm inequality, you can just bound that by operator norm of A inverse times norm of delta B. So if you change your right-hand side vector by 0.1 meters or whatever your unit is, and suppose the norm of your inverse is 20, then your solution might change by up to 20 times 0.1, which is 2 units, meters, or whatever. Okay, probably more interesting is relative errors, where you look at the absolute error in relation to the absolute size of the vector. So you're interested in the value that goes for the question mark here. And of course, a change of 0.1 meter is a lot if your vector is only 1 meter long, but is not much if it's 1,000 meters long. So it's actually more interesting to look at these quotients here and thereby say, okay, my right-hand side has changed by 0.1% or something. And then ask by how many percent might my solution change in the worst case. Okay, and for this question mark, let me start from b equals ax and then put norms here and here. And now, of course, we can again bound that by norm a times norm x. And if you divide that by norm x and norm b, you get the following. And now we have all ingredients to resolve this little mystery here, because we have this inequality. Let me label it by 1, and that new inequality, let me label it by 2. And if I just multiply them, I get the relative error in x, which is the product of these two left-hand sides here, is less than or equal to the product of the right-hand sides. Okay, and on the right-hand side, you see norm of A inverse and norm of A, and norm of delta B, and you divide by norm of B, which gives you exactly the relative error of your right hand side B. And here's your question mark. And instead of question mark, we will say condition number and abbreviate it by little kappa of A. Okay, and if you have a condition number of 5, so if the norm of A times the norm of inverse is 5, then that means 2% error in your right hand side can lead up to 10% error in your solution X. Okay, and now note that everything we did so far in this section still works when you replace the equals sign here in AX equals B by an approximately equals sign. The only thing that changes is that your solution operator is not A inverse then, but the more Penrose pseudo inverse. Let's write that down. Okay, so the condition number would then be defined with the pseudo inverse instead of the inverse, which of course covers the previous case where A inverse exists, because then it's equal to the pseudo inverse. Okay, let's close this short section with a little lemma that I already announced last week. If A is an operator in Hilbert space, then you can study the adjoint A star. And then, like I said last week, A star A, the condition number, is the square of the condition number of A. And of course, that's bad news, because if your condition number used to be 5, then it's 25, and your 2% error might be turned into 50% error, which is not great. And the proof is not difficult. So for the condition number, you need to look at the norm of the operator on brackets and the norm of the inverse or pseudo inverse of the operator on brackets. Let's start with the norm. Well, the norm of A star A is the norm of A squared. We did this, we showed this in exercise problem 7.c. Okay, now we just have to show the same for the inverses or pseudo inverses. So we know that the inverse of a product is the product of the inverses. And then it's easy to see that star and inverse commute, so you can do it in the other direction, in the other order. But then by problem 7c again, you get the norm of the inverse and then squared. Okay, and then of course you just multiply the left-hand sides, and that gives you the product of the right-hand sides, and that proves our claim. If this step here was not quite clear to you, then check this or ask me in the exercise session. Okay, so much about the condition number and why it is important.